Welcome to FRC log replay and simulation, taking the next step. Thank you all for coming or for staying after the last presentation. My name is Jonah. I am a computer science student at Worcester Polytechnic Institute. I am an alum of Team 6328, and I am currently a software mentor and a WPI Lib developer.
My name is Neil. I'm a sophomore, and this is my third year on the team, and I'm a software student.
My name is Manthan. I'm a senior, and I'm the software lead on Team 6328.
Yeah. I'll also note that this presentation is being recorded. It'll be available on our YouTube tonight if there's anyone that couldn't make it here. And for those of you that were not in the last presentation, you may notice that my voice is not great today, so I appreciate your patience if I need to take a pause from time to time. Okay. So here's what we're going to be talking about today. We'll start off by looking at what is simulation and go through some different simulation architectures. We'll talk about what AdvantageKit is and go through several case studies of that. We'll talk about modifying the past and what that means, go through a few more case studies, and then we'll talk about taking the next step. So to start off, this presentation is a bit different from the last one, for those of you that saw that. So before we start, I want you all to take a moment and think about what your goals are in watching this. Think about what you hope to take away. Now, for almost all of you, we expect that you'll see some hopefully interesting ideas. You'll see some of what's possible in FRC software, but even without implementing this stuff, you might get some new ideas and things to think about. We expect that for far fewer of you, you might actually be going on to try and implement this. And for those of you, this presentation is really just a taster. You're going to want to check the documentation, ask lots of questions, etc. But also keep in mind that a lot of the advice and the tools that we're going to share are really targeted at those who are excited to work through complex problems on their own. We are very much straying from the beaten path with a lot of this stuff. So you have been duly warned. Make sure that you are thinking about your own team's needs when you're approaching this.
So first, let's establish what simulation can actually mean in FRC. So our one-sentence definition for this is that simulation is testing code without a physical robot. And of course, we may be wondering, why is this helpful? Well, first of all, it allows us to develop code when the robot's actually unfinished. We all know it takes a few weeks for the CAD and design team to actually manufacture and work on the robot. So the time between those is actually very valuable, so we can get the fundamental code written, and we can just tune out the minor errors and PID, whatever minor changes have to happen with the robot. Because we want to maximize our available time with the real robot. At competition and at home, the time with our physical robot is very valuable. So we don't want to waste it writing the fundamental code. Instead, we want to be able to simulate and work out the minor changes when we don't have the robot, so we can just tune it to make our conceptual code fit the real robot when we actually have the robot. Finally, we want to be able to debug very quickly at competition. We don't always have physical access to our robot at competitions because the pits may close or maybe the practice field isn't open. So being able to use simulation allows us to access the concept of the robot and run kind of reviews on what's happened without the physical robot. How does this actually work? So especially coming from an industry, simulation can mean a bunch of different things. One, it might be running stuff on a different laptop. Without a RoboRio and without the physical capacity that the robot has, we have to be able to run it on our own laptop. And of course, WPI Lib has a great set of tools for this, so I encourage you guys to check that out. It also might mean using simulated hardware, because we don't actually have the CAN bus or the PWM outputs that are on the robot. So we need some way to mock or completely replace the stuff on the robot so you can run it on our laptop. Finally, it might mean that we want to simulate a physical environment that encapsulates everything that's happening conceptually on our laptop. That might mean that we have a full physics environment for every interaction on the robot, which sometimes can be a stretch in FRC. For this reason, industry usually covers all three levels of this, but in FRC we usually only need around 2 levels, which is the first 2 levels. However, for this presentation, we will be focusing on the 3rd level. So here's what our type of logging might look like. Rather than using a single simulated environment, we might use an individual simulated environment for each subsystem. The benefit of this is that each simulator can be much simpler, because we can also use classes that are provided by WPILib, for example, for a drivetrain, for a flywheel, for an arm. And we can still model what's happening to these physical artifacts when we apply voltage to them. However, the downside is that, of course, we can't simulate actual interactions between multiple subsystems. However, this is kind of rare because we usually only want to model the interactions that are happening within a single subsystem. For example, even if it's a complex thing such as a double jointed arm, we still only want to really model the stuff that's happening within the arm.
Before getting in too deep, let's talk about an example where this is useful. In 2023, we decided to build a triple jointed arm. Software-wise, this was going to be a big challenge, so we needed to start early. Simulation was the obvious choice for us. And so before we get to writing the code to control the arm, we first needed to simulate it. We implemented a physics model for a double jointed arm. Here's what it looked like. You can see that the joints interact realistically, speeding up and slowing down. You'll notice that this simulation, however, doesn't interact with the ground. This is the downside of not having a unified simulation environment, but it's good enough for almost any FRC environment. The robot should never put itself in this state, and we can verify whether it's working correctly just looking at it visually. Now we got to work writing the code to control this arm. The first step is getting the kinematics right. Throughout this process, we also developed a trajectory generator using numerical optimization. Lots of code development happened here. Remember, all of this was happening before the robot was even ready. So here's what the final simulation looks like. This is it running trajectories with a feed-forward model on PID controllers. The question is, does this match the real robot? Unfortunately, no. We made the simulation before the final design of the robot was created, so the inertia, the gearings, and etc. weren't quite right. However, the important thing is that the general concept was. This is still a triple jointed arm with the same number of motors per joint. Ultimately, a perfectly accurate simulation isn't really that useful. You end up spending all your time trying to make it match reality and keep up with changes when all you really want to make sure is that your code conceptually works. You still need it to work on the real robot. So here it is on the real robot. I'll note that we keep track of two different sets of constants when tuning this robot. See, the thing is, if the sim and the real robot don't match, we can't use the same gains. And having a simulation good enough to use the same gains as your real robot is very hard. This is why we store a set of simulated constants and real constants that we can tune individually.
Okay, so that's all good at a high level, but let's talk about how it actually works. Now, the core of the simulation is the physics model. And remember that here we're only talking about each subsystem being simulated individually. WPILib provides a number of built-in physics models. You can see some examples there. And all of these models are designed to take in a voltage and output a predicted subsystem state, so like a position and velocity. Those are based on a simplified model of how the subsystem works. So now that we can simulate the movement of each subsystem, how do we actually use that data? Well, most of your subsystems probably look like this, where you have subsystem code talking to a CAN-based motor controller. You're sending commands and probably reading back sensor values. So where does the physics simulation fit into this? Well, the first technique to solve this we'll call data injection. This requires support from the vendor. The way that this works is that they provide a sim object, which is connected to the real controller. You can then read the applied output from that sim object, run the physics simulator within the subsystem, and then write your simulated outputs back to the sim object. Those simulated outputs can then be read back through the normal interface. This is the structure that's recommended by WPILib and by most of the vendors, at least those who support it. But we're also going to talk about an alternative. That architecture is hardware abstraction. Under hardware abstraction, subsystems would instead look like this. So in addition to the core subsystem, you define an I/O interface. That contains methods for all of the inputs and outputs of your subsystem. So for example, you might have methods like set voltage or get position. You can then have multiple implementations of that common interface. For example, you could have a real implementation, which uses the motor controller object from the vendor, but you could also have a sim implementation, which runs the WPILib physics sim directly. You could then swap out those implementations, or you could even have multiple real implementations. Okay, so both of those architectures have their benefits, so let's compare them in a bit more detail. So first, for data injection. One of the key benefits of this is that you have access to vendor control loops. So you can easily simulate onboard controllers if you're using PID control or fancier control modes on your integrated controller. Some vendors also support high-fidelity CAN simulation. So the timing of CAN frames can be recreated in Sim. Another benefit is that you have a single class subsystem. Everything is stored in one place. But one downside, which you may have already picked up on, is that the data flow here can be pretty convoluted. It's really easy to mix up how data is supposed to move or read data from the wrong place. For example, if you read your simulated outputs directly rather than reading them through your controller object, you can end up with code that works in simulation but then doesn't work on the real robot, which is not ideal. Another downside here is that it very much promotes vendor lock-in. This structure is not supported by all vendors, and it forces you to choose a single vendor at the start of the season and stick with them, rather than choosing the vendor that's actually best for your team's needs. So what about hardware abstraction? Well, one of the benefits here is that it has a much simpler data flow. We find that it's easy to understand and easy for students to understand. Hardware abstraction is also much easier to break down in terms of code development. We find that new students are much more able to jump in writing code for subsystems when they only need to think about one interface or one implementation, or writing a subsystem without concern for the hardware. So it makes it easier to break up work and get new students involved. Another benefit is that you have vendor flexibility. Your sim is not tied to any particular vendor, and you can even have multiple real implementations. This year, our dev bot used all Spark Maxes and Spark Flexes, but our comp bot used Talon FXs. We were able to easily support both robots using the same version of code, using the vendors that we preferred. Now, the main downside of hardware abstraction is that you have lower fidelity vendor simulation. So if you're using vendor control loops, you may need to recreate them manually. For example, using WPI Loop's profiled PID controller rather than CTOE's motion magic. Now, recreating those vendor features well enough is usually not too difficult, and also keep in mind that recreating it exactly doesn't really matter as much when you aren't trying to match the sim to the real robot exactly and share gains between them. But overall, which of these is the right choice really depends on your team and what you're trying to get out of sim. Now, on 6328, we've used hardware abstraction for years now, and we've never looked back. But there is another reason that we really like hardware abstraction. You may notice this presentation was titled Log Replay and Simulation, and thus far we have only talked about simulation. So let's switch gears for a minute.
So log replay is where AdvantageKit comes in. AdvantageKit takes a step beyond just the normal physics simulation like what we've been talking about previously. This may seem unrelated at first, but we will return to our hardware abstraction. So for those of you that didn't see our last presentation, here are the 3 levels of logging: driver station logging, onboard logging, and log replay. We talked about levels 1 and 2 in our last presentation, and we'll focus on level 3 here. So level 3 logging takes the log everything approach, where you log the full internal state of the robot code, which is accessible using a log file. This means that there's no risk of not logging a field. However, it is more complex to implement. There are several tools available for this, including non-FRC frameworks like ROS. Today we'll focus on AdvantageKit.
Now, to understand level 3 logging, we need to simplify our view of the robot code a bit. So fundamentally, robot code is reading a set of inputs and producing a set of outputs. Inputs would be things like encoder values, joystick buttons and axes, the enabled and disabled state, other sensors, etc. The robot code then has a bunch of internal logic. So this is your timed robot, your commands, your subsystems. And then it produces a set of outputs. Those might be motor voltages, pneumatic commands, your odometry pose, your flywheel set point. Notice that we put the odometry pose in that list, despite the fact that it's not sent to any motor controller, because it's calculated based on input values. So relative to this, here's what level 2 logging would look like. So we might sample a few key fields from the inputs and outputs and save those to a log file. But of course, we can't look at any fields that we didn't explicitly log the first time around. So to fix that, here's what level 3 logging looks like. We'll break down each part of this. So instead of logging just a few fields, we instead log every input field. That's really important. Any data that the code uses needs to be logged regardless of its source. But why? Well, if you run the same robot code in a simulator and you replay the inputs from the log, the code will do exactly the same thing as on the real robot. That's sort of a wild idea, so you can take a moment to wrap your head around that. If we have the same code and it receives the same inputs in the same order, we know that it will always produce the same outputs, which means that we can measure all of those outputs from the simulated code and be guaranteed that they are exactly the same as they were on the real robot. We could even adjust the robot code in simulation to generate more outputs than the first time around, like data we forgot to include in the log file, but again, be guaranteed that those inputs are the same as they would have been on the real robot. Now, that's all good in theory, but let's talk about how it changes the robot code. AdvantageKit needs to be able to log and replay all of the code's input data. Now, lots of that data is managed automatically by AdvantageKit, like the robot state, joystick data, rheostatus, and power distribution data. It's also worth noting that timestamps are included in that list. AdvantageKit guarantees that all timestamps read during a single loop cycle are identical so that they can be replayed consistently. AdvantageKit produces what we call timestamp synchronized logs, which means that all fields are updated once per loop cycle, and each loop cycle has a single timestamp. Now, in order to guarantee that the data going to the robot code is the same as the data going to the log, AdvantageKit shims or replaces several WPILib classes to make this work. Now, the other side of this are any inputs that are part of subsystems, so things like encoders, gyros, limit switches, etc. And this is where hardware abstraction comes into play. So here, the I/O interface defines the input data for the subsystem. And when we're running on the robot, AdvantageKit records all of the input data coming through that I/O layer. And then here's the fun bit. When you're running a log replay, we just disable the I/O implementation, and AdvantageKit will provide all of the same data instead. The subsystem, and in fact the rest of the code, can't tell the difference between whether they're running on the real hardware or whether they're running in replay with AdvantageKit providing the data. So you get all of the normal benefits of hardware abstraction too. You could still write a physics simulator implementation and use that. Now note that in this case, when we're talking about AdvantageKit, simulation can actually mean two different things. One is that it could mean physics simulation running in real time, where the states of mechanisms are being calculated based on a mathematical model. But it can also mean log replay, where the states of mechanisms are based on a log file and there is no I/O implementation. Now, if you're curious about what the code for this actually looks like, I'd encourage
These studies can be based on our 2022 robot code, which ran on Bob Operations. And it was a West Coast drivetrain with retroeffective tracking with limelight and a flywheel and a motorized hood. So this can be a simple example of how we can extract an extra output that we had not originally logged by replaying the log. So we'll start by looking at one of our log files from our 2022 championship. So in this example, we're going to first add just a labeled status to the discrete field. We can drag out the flywheel goal, which is the set point. And the flywheel goal basically depends on the distance that we are from our goal. And this was something that we chose to explicitly log, so it was already there. So let's say we wanted to check that the relationship between the distance and our flywheel goal was accurate. Unfortunately, we actually forgot to log our distance from our goal. So this is what we're going to do. We're going to, since the measured distance was based on our odometry, which used our vision data, our wheel encoders, gyro, angle, etc. as inputs, and these are already logged, we can extract the measured distance from the inputs that we already logged. Except there is a single problem. Remember, from this diagram, we know that the simulated code would behave exactly the same given that it's the original robot code that was running before and that it receives the same inputs. The copy that we were running by the end of the off-season of 2022 was substantially changed by compared to what we were running at the time of this game. So since there are changes, we have to go back to the original commit that was running on the robot at this point. So a lot of luckily is based on the commit hash is the version of the code is checked by git control, so we can go back to it using the git hash. So each commit can be uniquely identified by its hash, which allows us to find a specific version of the code that's running on the robot at this time. However, there's a caveat that commits that aren't committed, or stuff that isn't committed to the robot code can't. Changes that weren't committed may be still deployed to the robot code. So we made an extension to this code where we have a separate system where every time we deploy code to the robot, it'll make a commit, so we can save what version of the code was running on the robot at that point in time. Here's an example of our commit log in 2023 champs. And you can see that we have the time which the commit was happening, which is when we deployed the robot. So, and these commits are put in on an event branch that we later squash into our main branch. So the result is that every version of code that ran on the robot is now saved. So using this, we can use AdvantageKit, which records the metadata from the log, including the hash, hash commit. And in this example, as we open the metadata tab, we can actually see that all changes are committed and into the git hash. We can return to this commit and guarantee that we have an accurate replay. So this is our 2022 robot code open in VS Code. We can add a line into the code to record the distance to the target in meters. And then we can run a git checkout to return to the old commit. And as we start the simulation, AdvantageKit will grab the last log from the Advantage code for convenience, and it'll begin replaying the log. Since it's running cycles as fast as the laptop panel instead of the RoboRio, instead of running the robot code every 20 milliseconds, it's running about 50 times faster because it's actually running on the laptop. And as a result is that we have this generated log file that contains original inputs, including the new replayed outputs. So back in Advantage code, we can open the new replayed log, we can open the log file, and now we have a new table that shows our replayed outputs, in addition to the real outputs that we were about earlier. And now we can use the target distance meters that we were checking earlier. This matches what data would have been on the real robot had we been logging. And we can confirm that our linear interpolation between our distance and our flywheel speed is in fact correct.
This is another example of how logging additional outputs can help diagnose issues. For context, our 2023 robot banana split could score anywhere automatically on the grid using its April tag localization data. This video is from an off-season event and will show a few examples of this system properly. The state of the auto-scoring system is shown here on pink, shown on the graph in pink. The driver pushes the right trigger to activate it. The rainbow LEDs activate. It drives automatically to the scoring position, and then it extends its arm. Here are a couple of examples of it working correctly. However, here's another example of the arm, of it driving correctly to the right spot, the arm extends, and it scores. The last example here, though, the robot drives to the correct spot, however, the arm doesn't extend. You can see we're frantically driving around trying to score this note. At the end of this match, we later confirmed that the arm was still moving, so this wasn't a mechanical problem. We confirmed that the driver was pushing the right button by looking at the logs. So we needed to track down the root cause of this problem. Here's a simplified flowchart of how our autoscoring command works. The trigger launches the autoscore command, which then launches two parallel commands. Drive to post, which immediately takes over the drive, and wait until command, which waits for a set of conditions to pass and then starts the arm path. These conditions are that the robot needs to be within 1.2 meters and 45 degrees of the target, 20 centimeters behind the charging station. We don't want to raise the arm in the middle of the field. The pitch and roll need to be under 2.5 degrees, and pitch and roll velocities need to be under 5 degrees per second. Autoscoring can take some hard turns, and we don't want to do anything that can make us tip while we're extending the arm. So perhaps one of these conditions wasn't met, but which one? Unfortunately, we don't explicitly log the status of these conditions. AdvantageKit can help. Using simulation replay, we logged all 6 conditions for ARM extension. Side note, this debugging work was actually done by a team member while they were on an airplane. This is an example of how it's supposed to work. Remember that pink just shows when auto-scoring is running. We've also plotted the elbow and shoulder shoulder set points to show when the arm is moving. At the position of this cursor, all 6 conditions are true and the arm moves. This is when it failed. Notice right here. The red shows when the pose is in tolerance, 1.2 meters and 45 degrees, and purple shows when the pitch angle is in tolerance, 2.5 degrees. Just as we're getting close enough, the pitch changes too much and stays that way, so the arm doesn't extend. Let's take a closer look at our pitch data. The pitch settles around 2.8 degrees, just outside of our 2.5 degree tolerance. So what was the cause? Well, actually, we were testing out our new TPU wheels at this event, which had a less stiff spring material between the hub and the tread. Because our robot had a slightly uneven weight distribution, one side of the robot was compressed more than the other, making us off-center. This could have been some mysterious fluke that was never solved. However, simulation replay gave us a definitive cause. We could have solved this by either switching wheels or adjusting our tolerance.
So those are both examples of how we can debug code using AdvantageKit, but that's actually not the only application for it. Because remember, all of our outputs from the robot code can be recreated in Sim. And theoretically, that means there's actually no reason to log any of them on the real robot. Now in practice, we generally do log the outputs from the real robot, so they're more easily accessible. That way we don't have to use a log replay just to see our estimated pose. But there are applications where you might want to focus on reducing the amount of work done on the Rio. Now in our last presentation, we gave some examples of how AdvantageScope can visualize game pieces. But let's say rather than a simple animation like we showed before, you developed a full physics simulator for shot trajectories, where you're accounting for drag, spin, angle, etc. Now that's very cool, and it's probably useful for debugging, but it may not be practical to run on the Rio. So what you could do is add something like this to the start of your simulation code. So when running on the Rio, it exits immediately, but when running in replay, it does the full calculation. It doesn't matter how slow that simulation is if it's running on a laptop. So this way you can get your high fidelity simulation and visualization without slowing down the Rio by just running the code in replay using a log file. So that's a potentially interesting application of AdvantageKit.
All of these examples involve running the same code on the real robot and in replay. This is probably the most common use of AdvantageKit, but you can actually modify the code. There are 2 restrictions to think about when doing this. First is that everything is connected. If you modify one subsystem, it may affect others in unexpected ways. For example, modifying your vision can affect your auto aim, which can then affect your flywheels and so on. This can also cause unexpected match behavior, for example, when you press a single button on your driver controller. Generally, it's best to focus on only modifying one part. Consider the replay bubble. This is a good way to visualize what AdvantageKit is doing. Some parts of the code can be replayed, but other parts cannot. The part that can be replayed can be thought of like a bubble. Anything coming into the bubble needs to be logged by AdvantageKit. Anything outside the bubble is free to read or write without logging, but cannot be replayed. Subsystems are in the bubble, I/O implementations are outside it. I/O interfaces define the boundary, for subsystems. When making modifications, make sure it only affects the robot code inside the bubble, so not the I/O implementations. There's lots of nuance with this concept, so let's take a further look. You're free to define the I/O interface however you want. Let's walk through an example. Most subsystems have a cascading set of controls. You have high-level control requests such as moving a swerve drive forward. Lower-level control requests can involve something like moving the first module at speed X. Feedback controllers such as position/velocity PID controllers, and motor outputs that produce outputs such as voltage or duty cycle. One option is to put the replay boundary here, where you run all your kinematics and feedback loops in the subsystem, where motor controllers only execute the final command. We did this on every subsystem in 2023. Another option is this. You run the PID controllers on a smart controller, and all kinematics happen in the subsystem. There's also some more nuance here. If you're running a profile, do you run it on the Rio or do you run it on the controller? This structure takes advantage of faster feedback loops, which allow most of the logic to be replayed. Here's the last option. Normally, we would generally recommend against this. However, there are some teams who have successfully used this. This is applicable with high-level libraries like Yaxle or CTRE Swerve, where high-level requests are replayable, but then passed off to a vendor library. The upside of this is that it takes advantage of existing libraries. However, important aspects of the code can be replayed, such as your pose estimation.
Now, even with those restrictions, there's a lot to be gained by modifying robot code. So we'll go through a couple of case studies of that. Now, managing vision data is one of the most common use cases for this. We can change our pose estimation pipeline, which is inside that replay bubble, and observe what new poses are produced. So here, going back a couple of years, this is our 2022 robot using vision data and a limelight to reset its odometry. So the green line shows when that reset is happening, and the green robot shows where it's resetting to. Now there's a fairly complex pipeline involved here, especially because we were using retroreflective tape, and filtering out invalid targets like reflections is critical. Now this match is an example of the pipeline working well. Now here's a different log from an off-season event where the limelight picked up some spurious targets. So you can see it jumps unrealistically across the field. Once the robot turns and it gets a better look at the target, we'll shift back to our actual position. So let's use a different AdvantageKit view to dive a little deeper. Now we're looking at the raw data from the limelight. Now to the right is an example from a different log of what this is supposed to look like. Each plus sign represents the corner of a detected target, which are the pieces of tape around the edge of the upper hub. And on the right you can see that they line up perfectly. But the image to the left is from the problematic log we just saw. Now clearly these are not valid targets, but they weren't filtered correctly, and so they messed up our odometry pipeline. So how can we fix that? Well, here we can use AdvantageKit's table view to inspect the data more closely. The highlighted line here is the set of x-coordinates for the points that we were just viewing, and it turns out that there are 13 corners listed. Now the corner count should always be a multiple of 4 if we're looking at rectangular pieces of tape. So, like before, we'll use the commit hash to return to this version of code, but instead of logging extra data, we'll add the lines shown here to the vision system. This will discard the frame if the number of corners is not divisible by 4. Now we run the code in replay as before, except this time we expect that the code's outputs will be different with the new filtering logic. So here's that same clip as before, where the green robot represents our replay. So we correctly reject the invalid target data, but once we get a good look at the target, you'll see that both poses reset to the correct place, so we're still accepting data that is correct. Now the neat thing is that we can run this version of code in future matches, even though we haven't tested it on the physical robot, because we know exactly what the code would have done if we were running a different version of code on the field. So this is super valuable at competitions where we may not have access to a practice field and certainly not a realistic environment with other robots. This is also useful for April tags too, not just retroreflective tape. Now in 2023 and 2024 we used 4 cameras on each robot and a variety of filtering techniques. But we were wondering how much those helped us, so we used log replay to check. Here you can see that the solid robot represents our standard pose estimation with 4 cameras and normal filters. The yellow ghost represents what our pose estimation would have looked like if we had 1 camera, but still with our normal filters. And then the red ghost is kind of fun. That shows if we had, with our 4 cameras, what if we were using very simple filters rather than our fully tuned version. And you can see that the solid robot is tracking much more smoothly and realistically than the other options. However, all of these filtering techniques didn't come out of nothing. We developed this over the past 2 years, relying very heavily on log replay. We were able to tune standard deviations, distance coefficients, extra filtering, all of that, based on real log data and looking what the robot would have done with different options if we were running all of those possibilities in a match. So AdvantageKit was really absolutely essential to us developing a robust pose estimation system.
But we don't have to limit ourselves to vision. This year we used, we can change the behavior of the arm instead. For example, this year we were using linear interpolation to map our distance from the speaker to our arm angle. And near the end of our linear interpolation, we didn't actually have any points. So points that were farther than around 4.5 meters, which is where we expected to be shooting from, didn't have a correlated arm angle. So the way that would look is that since there's nothing past 4.5 meters, there's nothing to interpolate between, so we're kind of stuck at this constant arm angle, which is not ideal. So when we were shooting from farther angles than we actually expected to, this was a very bad behavior. So we wanted the code to make a better effort at making a better shot. So we added a point over here at 8 meters, which is probably farther than we would expect to shoot from. And using this point, we can use the last 2 points to interpolate between any distances between 4.5 and 8 meters in order to get a more realistic arm angle. In retrospect, this wasn't great either, but we can see the change that this made to our actual behavior. Orange in this diagram shows the effective distance between the robot and the speaker in meters, and here's the cutoff of our original map, which didn't have the extra point at 8 meters. Purple in the diagram is our original arm angle, and green is the replayed arm angle. And we can see, as expected, closer than 4.5 meters, we're still interpolating between the same points, so they match perfectly. But farther than 4.5 meters on the left, they differ. The original one is constant at 25.6 because there's nothing to interpolate between, and our replay extends further down. So we changed the arm angle for our benefit. But it's still not great. It's kind of a naive way of deriving our arm angle. So instead, after the event, we made a better attempt at using a power function, and by fitting a trend line to this, we are able to make this function, which has a very R-squared, it's 0.99, and this is likely to be a better predictor of where we're going to be shooting, or how we want the arm to be shooting. And again, we can confirm the functionality of this by using replay. Purple is the original and green is the replayed, once again, and most shots match pretty well, under 4.5 especially. But the second from the left is the same shot that we were looking at last time, and it's taken from farther away than we would expect it to, and the power function produces a more realistic arm angle that we would rather shoot from. So we switched to this function, and we still use this type of thing to this day.
Okay, so we just covered quite a lot of ground, but this presentation is titled Taking the Next Step. And at the start, I asked you to think about your goals in watching this. Now keep in mind, AdvantageKit is very near the limit of what's possible in FRC simulation right now. But that doesn't necessarily mean it's the right step for you and your team. I would encourage anyone here to experiment with using data logging without AdvantageKit. There are a lot of options for that, which we covered in detail in our last presentation. You can also consider experimenting with physics sims using data injection. And if you're willing to stray a little further from the beaten path, you could try hardware abstraction or AdvantageKit for full log replay. But in general, all of these are really good as off-season projects. So you have a low-pressure environment to figure out if they are right for your team and for your students. Okay, so finally here are some links to a few of the tools that we talked about. You can also email us by contacting software@team6328.org. But thank you all for listening, and we have a few minutes to answer questions as a group.